So now let us go to the applications of Fourier series to PDEs, to the solving of partial differential equations. The three classical equations of mathematical physics are the Laplace's equation, the wave equation, and the heat equation. So here we shall see an application of Fourier series to solving the Laplace's equation on a disk and the heat equation with periodic boundary conditions. So the Laplace's equation, what is the Laplace's equation? Laplacian of u equal to 0. So what is the Laplacian? Del 2 by del x squared plus del 2 by del y squared plus del 2 by del z squared. But now we are in two dimensions, so there is no z component. So it will simply be del 2 by del x squared plus del 2 by del y squared. So what is the Laplace's equation? Del 2u by del x squared plus del 2u by del y squared equal to 0 on a disk D. What is the disk D? A set of all points x, y such that x squared plus y squared less than or equal to 1, the standard unit disk in the plane. The problem is to look for a twice differentiable function u which satisfies this equation. Of course, there are lots of solutions. For example, if you take any analytic function and take its real part, it will be a solution of the Laplace's equation. So what we need to do is to single out a unique solution by prescribing some boundary condition. So what is the boundary condition that we are looking at in this particular problem? U is prescribed along the boundary of the disk. Namely, the value of u is given along x squared plus y squared equal to 1. So you parameterize the boundary. The boundary is basically cos theta comma sin theta. So you have to prescribe u of cos theta comma sin theta, call it f of theta. Namely, f of theta is a 2 pi periodic function on the real line. So with this setup, we begin. The first obvious thing to do is to exploit the symmetry of the domain. The domain is a disk, and the disk is symmetric with respect to rotations which fix the origin. So we must employ polar coordinates. We must write down the equation in polar coordinates. Now it's an easy exercise for you to write down the Laplace's operator in polar coordinates. What does it read? It reads del 2 by del x squared plus del 2 by del y squared equals del 2 by del r squared plus 1 upon r del r plus 1 upon r squared del 2 by del theta squared. That's an easy exercise. I'll leave it to you to do. So what happens to the PDE? The PDE simply becomes del 2u by del r squared plus 1 upon r del u by del r plus 1 upon r squared del 2u by del theta squared equal to 0. Alright, so what do we do with this? Now we look for a special solution of the form v of r into g of theta, and we substitute v of r into g of theta for u in this last equation that you see on the slide. So what is it? U equal to v of r into g of theta. So del 2u by del r squared will be what? V double prime r into g theta. What will be del 2u by del theta squared? V times g double prime theta. That's exactly what you see. And then there is a del u by del r term. There is a del u by del r term, and that will simply be v prime r g theta. So put these in the equation and you get the following result: r squared v double prime plus r v prime by v equal to minus g double prime by g. But notice that in this equation, g double prime by g is a function of theta alone, whereas r squared v double prime plus r v prime by v is a function of r alone. The left hand side is a function of r alone, the right hand side is a function of theta alone. So both sides must be constant. Let us call the constant value k squared. So what do we get? We get a pair of ODEs, we get a pair of ordinary differential equations. r squared v double prime plus rv prime minus k squared v equal to 0, g double prime plus k squared g equal to 0. The second equation can immediately be solved. G of theta is c cos k theta plus d sin k theta, where c and d are constants. The first equation, r squared v double prime plus rv prime minus k squared v equal to 0. What is it? It is a Cauchy-Euler equation. So you must now recall how to solve a Cauchy-Euler equation. You must feed in the trial solution v of r equal to r to the power m. Then r squared v double prime will be m into m minus 1 r to the power m. rv prime is simply m r to the power m. So add them up. You get m squared minus k squared r to the power m. So the only possible choices are m equal to plus k and minus k. In other words, the only possible solutions are r to the power k and r to the power minus k. So v of r is a r to the power k plus b r to the power minus k. Now let us specialize further. G is a 2 pi periodic function. If G is a 2 pi periodic function, the k that appears must be an integer. C cos k theta plus d sin k theta must be 2 pi periodic, and that forces the k to be an integer. So k must be 0, plus minus 1, plus minus 2, plus minus 3. Look at the v equation. V of r equal to a r to the power k plus b r to the power minus k. If k were to be 1, 2, 3, what happens? We must now look at the b r to the power minus k. When k is 1, 2, 3, etc., r to the power minus k becomes infinite when r is 0. But r is 0 corresponds to the center of the disk, 0, 0. And my solution u is a twice differentiable function. So it must be finite near the origin. So the b must compulsorily be 0. There is no choice. So all we are left is capital A r to the power k. So multiply the two, and so we get the special solution to be r to the power k cos k theta with a c and r to the power k sin k theta with a d. And of course the c and the d will depend on k. So I should call it a k r to the power k cos k theta, b k r to the power k sin k theta, and k equal to 0, 1, 2, 3, etc. And because the differential equation is a linear differential equation, if I have a bunch of solutions, their sum will also be a solution. And so the most general solution is basically u equal to a naught plus summation n from 1 to infinity r to the power n into a n cos n theta plus b n sin theta. The last displayed equation in the slide is the most general form of the solution of the Laplace's equation, Laplacian of u equal to 0. Now we must bring in the boundary conditions. What is the boundary condition? U of cos theta comma sin theta is f of theta. U of cos theta comma sin theta equal to f of theta, as you see in the slide. We must now incorporate these boundary conditions, which means that in this last equation that you see on this slide, you must put r equal to 1. When you put r equal to 1, the left hand side is what? U of cos theta comma sin theta, that is f of theta. So we get the equation f of theta equal to a naught plus summation n from 1 to infinity a n cos n theta plus b n sin n theta. You see our good old friend, the Fourier series for the function f of theta. But f of theta is given to you. F of theta is a prescribed function. So once f of theta is given to you, the a0, an and bn can be computed. So here are some little exercises with specific f. So now let us try to solve the Laplace's equation on the unit disk with boundary value mod sin theta. So if f of theta is mod sin theta. Now the next exercise, show that if u is a harmonic function, that is if u is a solution of the Laplace's equation. The solutions of the Laplace's equation are called harmonic functions. Show that if u is a harmonic function, then the mean value of u along circles gives you the value at the center. So when you integrate u of r cos theta comma r sin theta d theta from minus pi to pi and divide by 1 upon 2 pi, you get u of 0, 0. In other words, the mean value of the harmonic function along a circle gives you the value at the center. This is called the mean value theorem for harmonic functions. Now let us proceed a little further with this. You see on this display f of theta and its Fourier series. The a0, an and bn can be computed in terms of f via those integral formulas for the Fourier coefficients. So now let us calculate these Fourier coefficients explicitly. Again recall, a0 is 1 upon 2 pi integral minus pi to pi ft dt. an is 1 upon pi integral minus pi to pi ft cos nt dt. bn is what? 1 upon pi integral minus pi to pi ft sin nt dt. Put these things in the first display on the slide. So you get u of r e to the power theta as a series, 1 upon 2 pi integral minus pi to pi ft dt plus 1 upon pi summation n from 1 to infinity r to the power n bracket cos n theta integral minus pi to pi ft cos nt dt plus sin n theta integral minus pi to pi ft sin nt dt. Now we must combine these integrals into one integral and we must exchange the integration and summation. You can do that because when r is between 0 and 1, your sines and cosines are bounded, r to the power n is rapidly going to 0 and the ans and bns are going to 0 by Riemann-Lebesgue lemma, and hence in particular they are bounded, for instance. So you finally get u of r e to the power I theta equals 1 upon 2 pi integral minus pi to pi big bracket 1 plus twice summation n from 1 to infinity r to the power n into cos n theta cos nt plus sin n theta sin nt. Cos n theta cos nt plus sin n theta sin nt is cos of n of theta minus t. And so what do we get? We must now find the sum of a series of cosines. We must now compute 1 plus summation n from 1 to infinity 2 r to the power n cos ns in closed form. That's a little exercise for you. You must go back to the previous modules. The very first module where we computed the Dirichlet kernel, remember? We summed a trigonometric series, a special trigonometric series. So you get 1 plus summation 2 r to the power n cos ns, we must compute. It is 1 minus r squared upon 1 plus r squared minus 2r cos s. That is easy to calculate, and I leave it as an exercise. So now we must incorporate this in the previous equation. What do you get? U of r e to the power I theta equals 1 upon 2 pi integral minus pi to pi 1 minus r squared f of t dt upon 1 plus r squared minus 2r cos theta minus t. Equation 2.11 on the slide. And let us look at this expression 1 minus r squared upon 1 plus r squared minus 2r cosine theta minus t. This expression has been abbreviated as pi sub r of theta minus t. This expression is called the Poisson kernel. This is called the Poisson kernel. So the solution has been expressed as an integral of f of t multiplied with this Poisson kernel pi r of theta minus t. You must compare this derivation with the derivation of the Dirichlet kernel of finding the nth partial sum of a Fourier series. There are features in common, but there is one crucial difference between the Dirichlet kernel and the Poisson kernel. Look at the expression again. R is between 0 and 1. So 1 minus r squared is positive. 1 plus r squared minus 2r cos theta minus t. That is also positive. So the Poisson kernel, unlike the Dirichlet kernel, is a positive kernel. This positivity of the Poisson kernel is very crucial, and it is what makes this whole business go through. Remember that the Fourier series of a continuous function may not converge, but here we are going to get convergence of this infinite series and of u of r e to the power I theta, and u of r e to the power I theta will give you back the function f of theta as r approaches 1. That is what you see on the slide. We still have to show that the solution obtained in the last slide does attain the value f of theta along the boundary, meaning u of r e to the power I theta tends to f of theta as r tends to 1. This is possible because of the positivity of the Poisson kernel. All that we need is f should be continuous on the boundary. So as I said, the Poisson kernel is non-negative. In the case of a Dirichlet kernel, we did an exercise. Integral minus pi to pi dnt dt was 1. The corresponding analog for the Poisson kernel is here. Integral minus pi to pi 1 upon 2 pi pi r of theta minus t is equal to 1. And the second exercise is what I told you, that u of r e to the power I theta does indeed go to f of theta as r goes to 1. The second exercise is not easy. It requires patience and a little thinking. That is why some hints are given to you. You try to do this. In any case, the detailed solution of this particular exercise will be available in the accompanying text. Now let us go from 2 dimensions to 3 dimensions. You want to solve the Laplace's equation in 3 dimensions for a ball, del 2u by del x squared plus del 2u by del y squared plus del 2u by del z squared equal to 0, and u on the boundary of the ball is prescribed, namely it is f, a continuous function. Now the analog of Poisson's kernel is also valid in 3 dimensions. 1 minus r squared upon 1 plus r squared minus 2r cosine of some angle. That formula exactly carries over in higher dimensional space, and the formula is 2.12, that the solution is given by u of y equal to integral over the boundary of B 1 minus norm x squared f of x dsx upon 1 plus norm x squared minus 2 norm x cos alpha to the power 3 by 2, where dsx is the area element. It is a surface integral over the unit sphere. F is given to you. And what is alpha? Alpha is the angle between x and y. While it is true that the formula carries over to 3 dimensions, the proof does not carry over. Fourier series in the plane and Fourier series in 3-dimensional space are quite different. You have to ask yourself, what is the meaning of Fourier series in 3 dimensions? There are several ways of looking at this problem, and the way to look at this in this context is to express the function as a series of spherical harmonics. Obviously the details cannot be carried over in this lecture series. I have given you a reference. G.B. Folland, Fourier Analysis and its Applications. It is reprinted and there is an Indian reprint available which appeared in 2012. Go to page 180 of this book and you will find a complete derivation of equation 2.12, if you will. Now let us go to the next important partial differential equation, the heat equation. So we want to solve the heat equation. What is the heat equation? Ut equal to Uxx, or del U by del T equals del 2U by del x squared. That is the heat equation. So let us take a smooth solution of the heat equation in the upper half plane, namely T non-negative. So x coordinate is the horizontal one and the t coordinate is a vertical one. T is greater than or equal to 0 is the upper half plane. Now you want to put a periodicity condition u of x comma t equals u of x plus 2 pi comma t for all x and for all t positive. Show that the energy, that is integral minus pi to pi u of xt squared dx, is monotone decreasing as a function of time. Let us look at the solution to this problem in detail. Call that integral minus pi to pi u of x comma t the whole squared dx as e of t. It depends upon t. You are integrated with respect to x, the result will still depend on t. So that is why you call it Et. Let us differentiate the energy Et. E prime t is twice integral minus pi to pi u of xt ut of xt dx. You take the derivative under the integral sign. Now what is ut? Del u by del t, but u satisfies the heat equation. So del u by del t equals del 2u by del x squared or u sub xx. So we get E prime t equal to twice integral minus pi to pi u of xt uxx of xt dx. Now we must integrate by parts. One derivative will shift from the uxx term and go to the other term. You will pick up a minus sign. You get E prime t equal to minus twice integral minus pi to pi u sub x squared dx. What happens to the boundary terms? The boundary term will cancel out because remember that the function that we are looking at is periodic. U of xt equal to u of x plus 2 pi comma t. If u is periodic, u sub x is periodic, u sub xx is periodic. So u times u sub xx is periodic, so the boundary term drops out when you integrate by parts. So what do we have? E prime t is less than or equal to 0, which means that E is monotone decreasing. So E of t is going to be less than or equal to E of 0 when t is bigger than 0. Anyway, the energy is non-negative, so we get the inequality 0 less than or equal to Et less than or equal to E of 0. So now suppose that initial value were 0. Suppose if u of x comma 0 is 0, then E of 0 will be 0. Then it will follow that E of t is 0 for all times. But E is a integral of u squared. So if E is 0, then the integrand has to be 0. In other words, u of x comma t has to be identically 0, right? Observe that the energy E is integral minus pi to pi u of xt the whole squared. So if Et is 0, then it is the integrand u of xt that must be 0. Alright, so from this uniqueness easily follows, as you can check. If u and v are two solutions with the same initial condition, then u minus v is also a solution with 0 initial condition. But with 0 initial condition, the periodic solution is unique. We have just seen that. So now we have proved uniqueness. We must go ahead and prove existence. The existence is via Fourier series. The solution that you are looking for, you simply write it as a Fourier series 2.13. U of xt equal to a naught plus summation n from 1 to infinity a n t cos nx plus b n t sin nx. The Fourier coefficients will depend upon t. Substitute 2.13 into the differential equation ut equal to uxx. Compare the like terms. You will get a naught prime t is 0, a n prime t is minus n squared a n t, b n prime t is minus n squared b n t. And so from these we'll immediately get a naught is constant, a n t is e to the power minus n squared t times constant alpha n, b n t is e to the power minus n squared t times beta n, another constant. So put t equal to 0 in 2.13, your u of x comma 0 is f of x. So what do you got? F of x equal to alpha naught plus summation n from 1 to infinity alpha n cos n x plus beta n sin x. Again our good old friend, the Fourier series for f of x, equation 2.15. But from 2.15 you can calculate alpha naught, alpha n and beta n using the formula for the Fourier coefficients, and you just have to construct your solution 2.16. Namely, u of x comma t is alpha naught plus summation n from 1 to infinity e to the power minus n squared t alpha n cos n x plus beta n sin n x. We still have to check that as t tends to 0 plus, the series on the right hand side of 216 does indeed converge to f of x. That is not altogether obvious, but if the function f of x is piecewise smooth and continuous, then the Fourier series converges uniformly. That's a theorem for which I have given you a reference to Bachman and Nariki's book, page 203. So once you have uniform convergence, you can exchange the limit and summation, and you can take the limit as t tends to infinity inside the summation and you get the result. Finally, there is an exercise for you to take a specific f of x equal to pi squared minus x squared, extend it as a 2 pi periodic function and carry out this program in this specific case. That completes this particular section on how to use Fourier series to solve specific differential equations. In the accompanying text, you will find more exercises with partial solutions and hence and such.